Welcome, I'm Bob McCarthy, and this video is a supplement to my book, Sound System Design and Optimization on Focal Press. It's entitled Understanding Phase, also known as How to Tell Time with Phase, or Converting Phase over Frequency to Milliseconds. The chart shown here is phase over frequency, and this is a picture of 1 millisecond of delay. How is that determined? That will be the subject of today's video. We typically visualize phase as a 0 to 360 or 0 to plus or minus 180 degree circular phenomenon, but there's more to it than that. You see, you work around the circle, and when you arrive back at 360 degrees, you're not in the same place as 0 degrees. In fact, you're a wavelength behind, as shown here by this spiral function, each spiral representing one wavelength behind. In order to view this spiral function in 2 dimensions, we're going to split the graph open at the bottom, putting 180 degrees at the top and minus 180 degrees at the bottom. You can see the spiral function starting to open up here, and in this chart you're able to see it move from 0 to 180 at the bottom, reappear at 180 at the top, crossing the 0 line representing 360 degrees or one wavelength behind. Then we cross a second wavelength, a third wavelength, finally a fourth and a fifth wavelength behind. The spiral has now been broken open into a series of diagonal lines and vertical lines that connect them. The diagonal lines indicate the phase shift as it's shown up in the number of wavelengths behind. The vertical lines are the connecting points of the broken open spiral that connect the minus 180 at the bottom to the plus 180 at the top. Notice that it's a constant angular slope. That constant angular slope is an artifact of the linear frequency axis display. Moving now to a logarithmic display over frequency, we can see that instead of the constant slope, we get an ever-changing slope angle which gets steeper and steeper as we rise in frequency. This is the result of the linear mechanism of phase shift being displayed in a logarithmic frequency axis. Moving now to the most basic way of how to tell time with phase response over frequency. This is a flat phase response over frequency, which means that there is no difference in time between the output and the input at any frequency. A second possibility of a flat phase response would be a flat inverted phase response, which would occur not at the 0 line that you see here, but at the minus 180 at the bottom, or it could occur at the plus 180 at the top. Either of those is a 0 amount of time shift. One is a polarity normal and the other is polarity inverted. In this next case, we see the phase angle falling as frequency rises. This is indicative of a delay. You see the wraparound of the spiral coming at the minus 180 and connecting to the plus 180, but that downward angle connotes a positive delay, also known as the output occurring after the input in this case. You could also find the phase angle for the same amount of time shift being upward, which means that the output is occurring before the input. Now, this might seem a little bit strange, but in two-channel measurement, it's possible at any time to find yourself with two channels that are out of sync. They could go out of sync one way or the other. The phase angle will tell you who's first. Moving on to 3 plots of phase over frequency, we will learn how to decode time by looking at the angle of the phase response. Notice that a similar pattern appears in each of the 3 responses, but it occurs in a different position, a different frequency range. That pattern denotes a constant slope angle, which, when it appears at a different frequency, means a different amount of time. The phase response angle relates to time over frequency. For a given phase response angle, the amount of delay is inversely proportional to frequency. In this example, we start with 0.1 milliseconds of delay, which is one wavelength at 10 kilohertz. And you can see the slope angle going down at about a 45-degree angle. The same picture appears in the middle of the screen at 1 kilohertz when we put in 1 millisecond of delay, which is also one wavelength. 10 milliseconds of delay creates the same picture at 1/10 the frequency, 100 hertz. So that is a picture then of one wavelength of delay. Whereas before we looked at a constant slope with different frequencies, now we will look at a constant frequency with differing slopes. The different slopes, of course, are the results of different amounts of delay. Our frequency is 100 hertz, and 10 milliseconds creates the familiar shape of a single wavelength, or 360 degrees. We will also look at the effect of 1 millisecond of delay, which is just 36 degrees, or 1/10 of a wavelength of delay. And finally, we look at 0.1 milliseconds, which is just 3.6 degrees of phase shift, only 1/100th of a wavelength, therefore an almost perfectly flat phase slope angle. These patterns play out again as we rise in frequency, with a comparable slope angle connoting a comparable amount of phase shift, the same number of wavelengths delayed, but a different amount of time.